Now that we've discussed running a thermal analysis, let's move on to conducting a thermal stress analysis. In this lesson, I'll give an overview of a thermal analysis that's been run on this brake disc, and we'll use the resulting temperature field to apply in a thermal stress analysis of this same disc. You can download the starter file below to begin. First, let's take a look at the thermal analysis that's been conducted on the disc. In the inputs section of the notebook, we can view some of the parameters that will drive our results. We'll begin by building our FE model off of this brake disc implicit. We'll mesh the body, create a volume mesh, and convert to an FE volume mesh. The selected material will be stainless steel from our material catalog. Then we'll move on to creating our boundaries and setting the boundary conditions for our model. We'll start by creating temperature restraints on the outer faces of the disc. And those areas will be restrained to this braking temperature of 150 C. For the inner exposed surfaces of the disc, we'll apply these convection boundaries. At these boundaries, the ambient temperature and the convection coefficient are driven by our variables from above. We'll create an FE solid component for our FE model, which consists of our meshed brake disc and our stainless steel material. We'll then add this FE component list to our model. We can add all of our boundary conditions that we created to a boundary conditions list and insert our model and our boundary conditions to this thermal analysis block. We'll view the results to the right, and we can pull the resulting temperature field from the properties list of our block details. We'll use this temperature field as our applied temperature load in our thermal stress analysis. Under our thermal stress analysis section, we'll drop a static analysis block from our simulation tab. We can go ahead and make this a variable called thermal stress analysis. Note that we can't use the same model as we did in our thermal analysis because we haven't yet defined thermal properties of our material. We can drop a new FE model block into our new section. In our FE components list, we'll add an FE solid component. And for our mesh, we'll use the same brake disc mesh as we used earlier. Now we'll need to apply a material with properly defined thermal properties. I'll add an isotropic material to our materials input. And I'll need to apply both the linear elastic and the thermal properties of stainless steel, as well as its coefficient of thermal expansion. I'll add two inputs to our isotropic material properties, and I can pull the first two inputs from our stainless steel variable above. When running a thermal stress analysis, we'll also have to pull the density of the material into our solid component. Our coefficient of thermal expansion can be entered as an isotropic thermal expansion block. And our alpha value will be 17.5 e to the negative 6. I'll make this into a variable called stainless steel coefficient of thermal expansion. And I can add this as our third isotropic material property. I'll drop this material into our materials section above. And I can make this new stainless steel material into a variable as well, calling it stainless steel thermal stress analysis. I'll make this FE model block into a variable called FE model thermal stress analysis, and I can drop it in as our model input in our static analysis block. Now we'll move on to creating our boundary conditions. I'll start by defining our initial temperature load. I can add an initial temperature block, and I'll set our initial temperature as our ambient temperature variable above. I'll call this variable FE initial temperature. Next, I'll define our applied temperature using an applied temperature block. And for our applied temperature, I'll pull in the temperature field that we created with our thermal analysis above. I'll make this a variable called FE applied temperature. Next, since this brake disc will be rotating, I'll apply a rotational force using a rotational force block. And for our region, I'll use an FE region by body block to choose all the cells in the entire brake disc. I'll use the FE mesh brake disc as our mesh, select the cells, and use the brake disc implicit as our body. I'll create an axis at the center of the disc, and I'll set our angular velocity using our disc rotation speed variable above. I'll make this a variable and call it FE body force. Next, I'll model the pressure from the brake pads on the outer faces of this disc by using two pressure blocks. Our first boundary has already been defined earlier in our workflow as FE boundary TA1. And our magnitude will be our brake pressure from our variables at the top. For our other pressure block, we'll use FE boundary TA2 and use the same magnitude. Now we've created these two boundary conditions with pressure facing the inside of the disc. I'll call these variables pressure 1 and pressure 2. And finally, I'll create displacement restraints at each of the fixed faces in the model. I'll also create one right at this center hole. I'll add a displacement restraint. Use an FE boundary by flood fill. Apply our disk mesh. Select our faces. And move our origin to where we want it. The first will be at the center hole. And we'll make the following 6 at the 6 smaller holes. We can do this by copying and pasting our displacement restraint and moving the gimbal around to select these 6 faces. Now that I've created all of these boundary conditions, I'll add them all to a boundary condition list and add them to my static analysis. I'll make this boundary condition list into a variable. And add it to the static analysis block. Viewing the results after this block runs, we see the displacement, strain, stress, and reaction forces from our applied temperature and other boundary conditions.